Today we're going to talk about the experiment LIBS, which is laser-induced breakdown spectroscopy. And we're going to use our instrument setup in order to determine the elemental composition of various samples, including metals and minerals. So the most important part about LIBS is that it uses a laser. So we have to always have our laser safety training and use all of the appropriate protocols, including a nice curtain to block out any stray radiation and then the appropriate eyewear. Now, the goal of the laser is to excite our sample. As our sample becomes excited and returns back to ground state, it's going to emit light that is characteristic to the elements that are present. So for example, sodium does a really good job of emitting light at 589 nanometers. So if we see that light being emitted, we know that sodium is present. So one other important aspect about the laser that we're talking about today is that it is a IR laser, so it is not visible, and it is pulse, which means that it could hurt you if you're not careful. So make sure you have your laser safety training completed and that your certificate is submitted before you come into lab. Okay, so we're going to first look at the samples that you're going to be analyzing in order to determine their compositions. And we have them all laid out right here for you. The first sample is going to be brass, which is a composition that's made up of zinc and copper, and we're going to use it to determine matrix effects. So we're going to take a measurement of that sample in air and then in a more dense material, argon. And then we're going to look at pennies. So we have old pennies and new pennies. Older pennies are a alloy of copper and zinc, where copper is by far the more dominant material. And new pennies are actually copper-coated zinc. So you're going to take a measurement on the surface of the penny, which will be mostly copper. And then as you continue to shoot the sample, you'll start to see zinc lines. Then what we'll do is we'll assign you an unknown, one of these electrodes, and you will tell us what metals are in the electrode. And then the last thing that you'll do is you're going to take a measurement of one of these minerals, and you're going to tell us what elements are present, and you're going to use that information and the morphology information, so its color and shape, and you're going to attempt to identify the mineral by name. When we're positioning our sample, we want to make sure that the fiber optics are close enough to the sample to collect the most amount of light, but also that the laser light is in focus with the fiber optics. So to ensure that this is correct, what we can do is alter the height of our fiber optics cable by using this knob on the side, which we call the Z-axis. It's important to understand that as the fiber optics cable is moving upwards and down, the horizontal axis is also changing. So what I normally do is I take a couple of shots with the laser and I collect the spectra, and then want to make sure that I'm as close as I can be while still having the laser light in focus. So after we've fired our laser, we are immediately triggering the computer to control our spectrometer system. So there's a very small delay on the order of microseconds between firing the laser and starting to take your spectrum, and that's just to make sure that the sample has enough time to start relaxing and emitting light. So as these fiber optics cables are going into our spectrometer, just keep in mind that we have 8 spectrometers that each cover a different part of the spectrum, and you can see the different sections and the wavelengths they're measuring labeled on the spectrometers themselves. So when we want to fire the laser, we need to make sure that we have a power supply that is able to control the system, and that's what this module over here does. So it has one lock that's in place where you need to make sure that you have the key to turn it on, and then another aspect would be of energy settings on this module. Normally we set it at 10, but occasionally the laser overpowers and overheats, and so we lower it a little bit. But if you look at it right now, we have no bars that are lit up here except for the 10. And over here we can see that it says stop and not run. So right now if we told the computer to activate the laser, it would not work because the module is not allowing it to work. So we're going to press run, and you can see that all of the bars are now lit up. And that means that if we were to fire the laser using the computer, it would now be able to take a measurement. Another aspect of the laser safety is that although this is a class 4 laser, we have an interlock system to protect us. So whenever this magnetic door opens, it'll trigger our module to turn off. So it's no longer lit up and we're now in the stop position. Now this is somewhat confusing for people because when you replace the sample and you open the door, you could potentially forget that this has that default built in. So when you try to run the laser and you see no light or hear no zapping noise, that's the reason why. So all you do is you reclose the door and you press run again. Okay, to take our measurement, we're going to follow the instructions on our instrument card. So it'll walk you through it, and your TA will help you as well. But what I wanted to point out was what a good spectrum looks like versus what a poor spectrum looks like. So right now, what you see is the different sections of the spectrometers are color-coded. So this is the first spectrometer, second, third, fourth, fifth, sixth, seventh, and eighth. And right now, it looks like you have signal, but that's misleading because we're actually zoomed in pretty closely, and this is the baseline for each of those spectrometers. So these actually have no chemical information whatsoever, and that's because I intentionally misadjusted the z-axis so that we're not collecting any light from the laser. It is very important that you know the difference between a good spectrum and a bad spectrum, because when you go to do your data analysis, specifically in our Python code, if you have something that looks like this, you'll find no lines and you'll be very confused. So let me show you what a good spectrum looks like. So I'm going to readjust the z-axis so that our laser will be in focus, and I'm going to take another measurement. Give it a second to display on the chart. So notice here, this is better because you can see distinct lines that are rising above the baseline level, but it's still not great. So I'm going to move up a little bit more and try one more.